SwayamPrabha. Digital India. Educated India.
Good morning everyone, welcome to week number 11. Now this is week 11, that means we are approaching the end of this course and this is the penultimate topic that we have to discuss here. Over last 3 topics we had quite intense discussion over 3 parameters or measurement of 3 parameters which are very common to our day to day application, industrial applications. Even layman also needs to have knowledge about the values of these parameters, namely pressure, flow and temperature, where we have discussed in detail about different possible types of measurement that we can have, and accordingly different categories of instruments we have talked about, particularly the ones which are most common. Now in this week we are going to talk about the motion measurement. Because of the intense nature of the discussion in the previous weeks and also considering that we are approaching the end of the course. So this week and also in the coming week I shall be keeping the discussions quite short and brief, talking only about the most important points or touching upon only the most relevant points related to the measurement of motion in this week and certain special topics in the next week, instead of going into too much detail of the relevant measurement systems. Now the term motion here I have to clarify at the beginning itself. Here we are definitely referring to some kind of velocity or acceleration measurement, but that does not relate to any kind of flow situation, because the measurement of flow velocity or fluid velocity in a flow we have already discussed in the concerned week or during the concerned module. If you remember, there we have talked about pitot tube. Now pitot tube, though it is actually a pressure measurement instrument or it actually senses pressure, but using pitot tube, or to be more specific using the static pitot tube, we can actually get a direct measurement of the fluid velocity, and that is the most common type of flow velocity measurement option that we can get. Similarly, we have talked about anemometers or mass flow meters, where we definitely get the mass flow measurement, but if we have idea about the density of the flow or density of the fluid which is flowing and also the cross section area of the duct, we can calibrate the same directly in terms of fluid velocity. Also we have talked about very enhanced measurement systems like LDV, laser Doppler velocimeter, or PIV, particle image velocimeter or velocimetry, both of which gives you a direct representation of the velocity vectors in a particular 3-dimensional flow field. So the measurement of fluid velocity we have already covered, both simple and complicated type of instruments. Similarly, we are also not going to talk about the flow of, or I should say the velocity of any rigid body motion. Like when a rigid body or particle is moving somewhere, the measurement of its velocity is primarily related to the displacement measurement, because once you know the displacement with respect to time, you can easily get velocity from there. Like in one of the earlier weeks, in week number 4, we have discussed about the circuits or data processing circuits like differentiators and integrators, and from that knowledge you know that once we have suppose the measurement of displacement in form of an electric signal, then we can easily use a differential amplifier, or I am wrong, differentiating amplifier I should say. We can easily use a differentiating amplifier or just a differentiator, which will actually give you the derivative of the input quantity, that is the derivative of the displacement, which is nothing but velocity. So such particle velocity also can directly be measured using those instruments. Here our discussion will mostly be revolving around vibration, picking up vibration and measuring the magnitude of corresponding vibration velocities or velocity of the platform which is vibrating and corresponding acceleration. So the term mechanical motion generally can have several kinds of applications, means just the way you would like to visualize this, accordingly all of them can come under this mechanical motion. But before I move forward, I have to clarify between two terms, which are sometimes used quite interchangeably. One is vibration, other is shock. Vibration basically refers to a motion which has some kind of repetitive nature. The amplitude may be changing, but it should be some kind of repetition of over this entire, there should be some kind of repetitive structure, repetitive nature over the entire span of discussion. The like say if a system is forced to vibrate, you may see an waveform like this with the amplitude continuously decaying, finally going back to the stable situation, but the repetitive nature is there, which may not be the case in case of a shock. In case of shock, you may get a sudden disturbance in the flow stream, and then it decays quickly to go back to the original situation, which is not truly the case in case of vibration. In case of vibration, if there is not sufficient damping provided, then you will get a continuous waveform moving continuously with the same amplitude and frequency over infinite period of time, which is not the case in case of a shock. So, we are going to primarily focus on this kind of nature, where we can have a periodic movement over a long period of time, which is we are calling as vibration. Now, as I mentioned, mechanical motion can have different types of description. So, all these four can come under mechanical motion, which I am going to talk about. Like if I say displacement, then we know that suppose in a linear motion, displacement generally we represent as S, which can be a function of time depending upon the system that you are dealing with. Similarly, in case of an angular system or angular coordinate system, if you have to deal with, then we commonly use the symbol theta to represent this. So, this displacement definitely is a kind of motion that we have to deal with, but quite often instead of displacement we talk in terms of velocity. Velocity v is nothing but the differential form of displacement, whereas in case of angular coordinate system we generally use the symbol omega to represent the angular velocity. Mechanical motion can also relate acceleration. Acceleration A is again nothing but dv dt, or we can write the second derivative of displacement. Similarly, if alpha is the symbol that we use to represent angular acceleration, this is just d omega dt or d2 theta dt2. So, whenever we are talking about the measurement of mechanical motion, we may be talking about measurement of any one of the three: displacement, velocity or acceleration, or maybe more than one, means your system may be simultaneously giving a measurement of both displacement and velocity. But there is a fourth one also, which we may need under certain situation, which is called jerk. Jerk is the rate of change of acceleration in both linear and angular coordinate system which you are dealing with. So, sometimes in certain situations we may also have to deal with a jerk, particularly when designing mechanical or structures or large civil structures. So, your mechanical motion related discussion can involve any one of the four, measurement of any one of the four or more than one. But in this particular week we are focusing primarily on measuring the velocity and acceleration associated with a vibrating member. And for that purpose we can use two kinds of instruments, one is vibrometer, other is accelerometer. Vibrometer actually is the one which relates to the measurement of velocity, accelerometer is the one which relates to the measurement of acceleration. Truly speaking, a vibration pickup or vibrometer and an accelerometer has nothing different in terms of their working principle. Their major difference will be coming in terms of the secondary transducer that we shall be using to get the final output. Like generally all these devices have two transducers in sequence. This is the primary one and this is the secondary one. Primary one we invariably will take the input and convert this one to some kind of electrical output, which is going to the secondary one. Now, depending upon the nature of the secondary one, the same device may act as a vibrometer, or I should say the same primary transducer may act as vibrometer or accelerometer. Like suppose you have already studied about displacement measurement. So, if I relate to that, if your secondary transducer is a potentiometer, or if your secondary transducer is an LVDT, then the output that you are going to get, that is velocity. So, if this secondary transducer is a potentiometer or a linear variable differential transformer, then you are going to get velocity as the output. However, if this secondary transducer is a variable reluctance type, like something like an inductocene, then what you are going to get, that is acceleration. So, by changing the secondary transducer, the same primary transducer can be used to act either as a vibrometer or an accelerometer, or I should say this may not be the perfect description. Let me be consistent with our earlier discussion. Let us say the potentiometer and LVDT, if you are using the secondary transducer, you are going to get displacement, and then this displacement using, because potentiometer the true output is displacement, and generally this secondary transducer is connected with a differentiating transducer or differentiating amplifier or a differentiator. So, we get velocity as a final output. So, truly speaking, a secondary transducer is going to get displacement, which will subsequently be converted to velocity using the differentiator. Whereas, if you are using inductocene, you are going to get velocity, and that will be scaled or differentiated to get acceleration. Whereas, we can have separate accelerometers also, where the output is directly acceleration, and we do not have to bother about the nature of the secondary transducer. Now, elementary vibration detectors, we can talk about two different kinds of instruments or techniques, I should say, which can give you very elemental identification whether there is vibration present in a system or not. But before I mention about any technique, I should say the most common or most efficient vibration sensor that we have is nothing but our skin or our touch, our sense of touch. Human touch can sense vibration amplitude as low as 0.3 micron. This is just by touching something, like if this particular pen is vibrating and if I touch it very loosely, even a vibration of the amplitude 0.03 micron can be sensed properly. Whereas, on the other hand, if I grip it tightly, it is a much stronger grip. In that case, the amplitude of vibration that we can pick up can be even smaller, something in the range of 0.025 micron, that is at least one order smaller than this. And no instrument that we have at present can sense vibration efficiently with this level of amplitude. So, human touch is probably the most efficient way of sensing vibration, but practically we need some kind of options to measure or quantify vibration, and therefore, there are several common kinds of instruments we can have. The vibrating wedge is nothing but a triangular shaped wedge, something like this, which is mounted on a surface, and this particular surface, when it comes in contact with any vibrating member, this particular surface, then this wedge keeps on vibrating, and as the wedge keeps on vibrating, its position keeps on changing continuously. So, let us say at as the wedge keeps on vibrating over a range, then let us say this is the extreme position of this topmost edge, the highest position that the topmost edge of wedge can have, and this is the lowest position. Then if it is vibrating quickly, let me draw the lowest position of this wedge as well. So, this is the wedge when it is at the lowest possible position. That is fine. So, what is the distance between these two peaks? This is the one. What this one signifies? This is definitely amplitude of the vibration. So, if we measure this one, then we can or measure or get an idea about these two extreme positions, or maybe get a photograph of this, then we can directly get the peak to peak amplitude for this. Here of course, the direction of motion is this much. So, this mechanical wedge or vibrating wedge is a very simple way of giving you the direction of motion and also an idea about the peak to peak amplitude. However, we are not going to get the waveform from this, and also not too much idea about the frequency of these oscillations, because it is not possible to count the number of oscillations this wedge is having over a given period of time. So, the most common method of measuring frequency can be a cantilever beam, can be the use of a cantilever beam or a cantilever beam of variable length. Suppose this is the member which is undergoing certain kind of vibration, then what we are going to do is that we are going to get this cantilever beam in contact with this particular body, and then using some suitable technique we are going to change this length. Now, the beam itself has some natural frequency, and as the length changes its natural frequency is going to change. Now, if we keeps on changing this length slowly, then we may reach a point where the natural frequency of the beam and the frequency of vibration of this platform, this member, they becomes equal to each other. So, then there will be a resonance happening and the beam will start to oscillate with very large amplitude. So, we can get an idea about the frequency of the beam from corresponding to that frequency of the member, the object, corresponding to the natural frequency of the beam with that particular length when we have very large amplitude oscillations. So, these are very simple way of measuring or detecting vibration, but the most common way of doing this is the use of seismic transducers. A seismic transducer is nothing but a spring mass damper system. Here we have a large mass generally called a seismic mass given by m, there is a spring, let us say the spring is having a constant k, and we are also having a damper, let us say the zeta is the damping coefficient. So, this entire assembly is located inside a house, and we are having this workpiece which is the one that is undergoing oscillations. So, from this particular assembly we can easily get an idea about the vibration or the entire nature of vibration, the amplitude, its oscillation frequency, and also the nature of the waveform using a simple arrangement like seismic transducer. Depending upon the configuration of transducer, it can be used as vibrometer or accelerometer. Like if you are looking for velocity measurement, then it will work in a displacement mode when we need to have a large value of m and a soft spring. Whereas, if we are looking for acceleration measurement, then the mass should be smaller and the spring should be much stiffer for this, but working principle remains very much the same. Let us quickly check the working principle. Let us say this is our mass m and we are drawing a free body diagram. Then under certain situations, what are the forces acting on this? Let us say this direction indicates x. So, under a certain situation, the spring force is acting there, or if I say this is the spring force, it is also the damping force can also be there. Of course, the direction of both the forces will depend upon the direction of motion, and there will be an inertia force also. This inertia force is the one that is opposing the motion of this against the vibration. So, under equilibrium condition, the summation of all these three forces has to be equal to 0. Now, what are the magnitude of these forces? The spring force, if x is the amount of displacement the body is having, then the spring force will be equal to k into x. What about the damping force? The damping force will be the damping coefficient into velocity, that is we can write damping force into dx dt. Now, instead of writing s, let us say x is equal to Sm, which refers to displacement of the mass. Then let us replace this x with Sm. Sm refers to the displacement of the mass. And what about the inertia force for this mass? The inertia force for this mass will be equal to m into its acceleration, that is we can write m into the second derivative of the displacement. So, if we put all of them together, then what we are going to get? Putting all of them together, we have Fi inertia force plus the damping force or viscous force plus the spring force is equal to 0, that is the inertia force m into d2 Sm dt2 plus dsm dt plus Ksm is equal to 0. This is very much the equation of a second order system, but Sm is the displacement of this mass m, but we are not interested to know the displacement of this mass m, rather we are interested to know the displacement of the member which is having this displacement. Like if we go back to the previous slide, this is the mass m that we are talking about, but our interest is about this workpiece. So, let us say Sm refers to the displacement of the workpiece, then let us say S refers to the displacement of the subject or of our object, because Sm already we have used. Then if Sr indicates the relative displacement between the two, then what will be Sr relative displacement of the mass with respect to object, then Sr will be equal to Sm minus Ss, or Sm will be equal to Sr plus Ss. So, if you take this here, Sm is getting replaced by Sr plus Ss, Sr plus Ss k into Sr plus Ss is equal to 0. Now, the member is not at all affected by the spring or the damping force or the subject, and accordingly our equation gets modified to 2Sr dt2 dsr dt plus Ksr is equal to minus of m d2 Ss dt2. Now, let us assume something. Let us assume that the member is undergoing a simple harmonic motion. Of course, simple harmonic motion is not possible in practical situations, and so the one final value or expression that we are going to get, that will be application of that will be quite limited. Still, that can give you some important insight into what is going to happen. It is quite similar to the way we have analyzed the generalized second order measuring instrument in the second week during the second module, but as that was quite a few weeks back or a couple of months back at least. So, I am doing the exercise again, and also to show you the relation between this member displacement or object displacement with the mass displacement. So, we are assuming that this mass or object Ss is undergoing a simple harmonic motion of the form say SSO into cos omega t, where omega is the frequency of oscillation and SSO is the amplitude. So, if we put it back here, or before putting back here, if we differentiate this, so it will become minus SSO omega sin omega t, and if we differentiate it once more, minus SSO omega square sin omega t. So, putting it back here, we are having this as m into SSO omega square cos omega t. So, this is a second order system that we are dealing with, very much a second order system, and we have to get a solution for this when it is subjected to this kind of simple harmonic motion. We could have also chosen instead of choosing this particular waveform, we could have also chosen a step input or something like this, but as we are talking about vibration, so the simple harmonic motion is the most idealized input that we can have for a system. Now, the solution for this one is quite standard, and I am sure you already know the solution for this particular system. To simplify this, let us divide this entire equation by capital M, so that we have d2 Sr dt2 plus Im Sr dt plus k upon m is r is equal to SSO zeta square cos omega t. So, it is a very standard second order ODE which we can solve using any standard boundary condition, but before if we from there we can easily write that the standard from SRT will contain two parts, one exponential part and another transient part which is of importance generally, where the exponential part will be having some constant. I am not writing the detailed expression, you can go back to week number 2 or can refer to any standard textbooks where it will be having minus t upon tau, where tau is the time constant, and in this particular case your time constant will be equal to twice of m upon zeta. And the one that is of major importance to us is the second part. In the second part we are having m SSO omega square upon k into cos of omega t plus phi, where phi refers to the phase angle, divided by root over 1 minus omega whole square, this whole square plus 4 plus it will be equal to 2 zeta by omega whole square. Here this omega refers to the natural frequency, we can also write this one to be omega n, just to clarify that we are talking about the natural frequency, and omega m, can you identify the omega n from this equation, this particular equation that we have written from there? It is very simple, it will be root over a naught by a2. So, from there it becomes root over k by m, and so if we are talking about when t tends to infinity or t is a large time, this exponential term drops out and we are left with SRT to be equal to some SR0 into cos omega t. This omega is wrong, this should have been the capital omega, which is the frequency of the vibrating member, omega t plus phi. Here SR0 is the amplitude of oscillation of this relative displacement. So, this is equal to m by k we can represent as or k by m can be written as omega n square. So, this becomes SSO into capital omega by omega n whole square into 1 minus omega upon omega n whole square plus 2 zeta omega upon omega n whole square whole to the power minus half, and this phi is the phase difference that is going to get introduced because of the action or presence of all this mass and damper and the spring, and so it will be equal to tan inverse of 2 zeta omega n divided by 1 minus whole square. Here of course this zeta is the ratio of the damping coefficient to the critical damping coefficient that you may have the system. Truly speaking, I should have made another change also, where this term should have been, and also here there should have been zeta only, this ratio this. So, this is a very standard mathematical practice to get the waveform for this corresponding to the relative displacement. Now, we have the amplitude of this one and frequency for this one, but you have to consider that here you are talking about when you have progressed a bit in time, so that the exponential part has dropped out and we are left with only this so called near steady state or stabilized part of the displacement. Now, here there are several points to look for, like look at the expression for this SRO. Now, here the natural frequency and the value of this zeta, they are all or they are both can be altered at the design level of the seismic instrument itself. So, omega n and zeta are given, then everything comes to the value of this capital omega that you are introducing, or in a way the ratio of omega upon omega n, everything becomes dependent on this frequency ratio. Ratio of angular frequency or just normal frequency, everything comes dependent on that for both amplitude and phase response. Now, we have earlier studied the standard amplitude and phase response for instruments, for second order instruments, more a repetition of the same thing. You can see as the frequency ratio keeps on increasing, the magnitude or the amplitude, you can say this one can be viewed to be a representation of SRO divided by SSO. Actually, I should have given a plot of SRO by SSO directly. If I represent that in this way, say SRO by SSO and divide here omega upon omega n separately, then you will find that for small value of zeta you may have a profile somewhat like this, or it should not be such sharp line, but as zeta keeps on reducing it becomes more moderate. This for very high value of zeta it is just trying to approach this, and this particular level is 1. So, interesting part is as the omega keeps on increasing, frequency keeps on increasing, typically when omega capital omega is about 3 times for this, then everything is quite close to 1, and so that is something quite desirable. And these are the zeta values, zeta keeps on increasing in this direction. So, we have to choose the damping also accordingly, because damping has a critical role to play. Similarly, the phase difference for frequency ratio omega upon omega n equal to 1, we are having a 90-degree phase difference between the two, and this ratio of these two frequencies, this particular thing has to be taken into consideration. Like we can check one numerical example. Suppose let us say for a certain situation, for a certain seismic instrument, we have zeta given to be equal to 0.68, and it is given that the amplitude of this SSO is something like 0.015 millimeter, extremely small oscillations it is having. The natural frequency has been measured to be 4.75 hertz, whereas the excitation frequency is given as 7 hertz. Now, we have to estimate how much error may get introduced if we directly take this SRO to be equal to SSO. We have, for that we need to, because this is the actual amplitude oscillation that is happening, but your SRO is slightly different. So, now what is the frequency ratio here? Here Fe upon Fn can be taken to be equal to, using suitable conversion factor, we take this one as omega upon omega n is equal to 4.75 by 7. I have pre-calculated a number to be 1.474. So, if we calculate now SRO using the expression provided in the previous slide, so we have SSO into omega n whole square divided by root over, just referring back to the previous slide, look at this expression. So, we have this thing root over 1 minus omega upon omega n whole square, this entire thing to be whole square, plus 2 zeta upon omega n, again this entire thing to be equal whole square, and if we put this number, you are going to get this RO to be equal to 0.014, something like this. So, how much error that gets introduced? So, percentage error, if we take this one to be the correct reading instead of taking this one, then the percentage error that is getting introduced is mod of 0.015 minus 0.014 divided by the true one, that is 0.015 into 100%. This will roughly be coming around 6.3% approximately. So, about 6% error gets introduced, because we are taking the amplitude of this relative displacement to be equal to the amplitude of the true member displacement. But if we have proper idea about this particular omega upon omega n, then we can easily do this correction to get the final value properly. Means we can easily use this value of SRO to get the value of SSO. So, this is the mathematical base for any seismic instrument. As I have promised, these lectures I shall be keeping quite short, and that is why today I am going to finish it here itself. In the next lecture I shall be discussing slightly more about a few other vibration related instruments. So, we today talked about different kinds of mechanical motion. We have seen that displacement, velocity, acceleration and jerk all comes under this category of mechanical motion. Then we have talked about vibrometers and accelerometers, where difference is mostly in terms of the secondary transducer that is used. Like with the same primary transducer, if we use an LVDT, that will act as a vibrometer, giving a displacement and subsequently getting converted to velocity, whereas if you are using an inductocene, we can get velocity which can be converted to acceleration. Then we have talked about the elementary detector in two forms: the simple wedge, which generally gives the amplitude of oscillation but not frequency. To get the frequency, we can use a simple cantilever beam of changing length. And then very basic discussion about seismic transducer we had today, where we mostly focus on mathematics. Most part was a repetition of what we discussed earlier about the response of a second order transducer against simple harmonic inputs. So, that is it for the day. I would like to discuss a bit more on this in the next lecture. Till then, goodbye.